Imagine querying a banking AI for RBI guidelines launched just yesterday. Instead of admitting it lacks data, the system confidently invents a completely fake rule. At their core, out-of-the-box large language models are stateless. They function as next-word predictive engines, restricted entirely by the boundaries of their initial training memory. Taking a raw LLM and asking it factual questions is like forcing a closed-book exam. Retrieval-Augmented Generation provides an open-book alternative. The system actively searches an external database, finds the relevant document, and requires the AI to base its generation on that specific factual source. Relying purely on an LLM's internal memory and a production enterprise environment mathematically guarantees failure. Citation transforms the system from a toy into something legally verifiable. A common mistake among junior engineers is attempting to solve hallucination by fine-tuning a model on company data. Fine-tuning requires spending thousands of dollars and hours of computational processing to retrain an entire mathematical structure just to update one corporate policy. Consider an Indian enterprise updating its Diwali leave policy guidelines. Cultural events and corporate rules evolve rapidly. A fine-tuned model becomes outdated the moment the HR department changes a single paragraph. RAG operates with complete modularity. You delete the old PDF from your database, upload the new one, and the AI immediately applies the new rules. No retraining is required. Most failures in enterprise AI originate in the retrieval architecture, even when the language model itself is innocent. Building enterprise AI requires a rigorous 8-step pipeline, starting with the rule, garbage in, garbage out. The real-world data at Node 1, Ingestion, is unstructured and hostile, trapped in dense PDFs, dynamic websites, and mixed language documents that standard loaders extract as pure noise. Top engineers bypass standard scrapers by deploying specialized ingestion tools like LangExtract and Selenium URL Loader. These render hidden browser pages and structure messy data before it even enters the pipeline. Once ingested, the data hits Node 2, chunking. Embedding models have hard token limits. You cannot feed a 500-page manual into the mathematical engine all at once. Standard character splitters often cut sentences in half, destroying the semantic meaning of the text. Instead, NLP splitters analyze the actual syntax to divide the text by logical paragraphs and complete sentences. To prevent information from being lost at the cut, engineers apply chunk overlap. By duplicating the end of one chunk at the start of the next, you preserve the semantic tissue. If the physical data structure is broken at layer 2, the final prompt generation at the end of our 8-step pipeline will mathematically fail. At Node 3, we handle embedding. This process converts human text into massive arrays of numerical vectors, assigning a mathematical coordinate to every concept. Modern multimodal engines push this further. They embed PDFs, raw audio files, and visual stock charts into the exact same mathematical space. These vectors are stored in Node 4, the vector index. When a user asks a question, the system uses approximate nearest neighbors to calculate the spatial distance between the query's vector array and the millions of document arrays in the database. This process faces an immense challenge in high-stakes environments. If an AI lawyer needs to navigate decades of dense judicial code to find a specific ruling on fraud, semantic meaning alone is insufficient. For the Indian Supreme Court, transitioning to the new BNS legal framework, searching pure text returns a chaotic mix of obsolete and active law. The solution is metadata extraction. By attaching digital tags, like the year 2024 and Section 318, to the chunks during ingestion, the system ignores mathematically similar but chronologically obsolete data before performing a single vector calculation. Filtering by metadata prior to semantic search drastically reduces computational cost while guaranteeing factual relevance. At Node 5, retrieval, the system must balance finding the absolute correct information with ensuring a diversity of context. To solve this, engineers use the maximal marginal relevance algorithm. MMR actively suppresses redundant chunks, ensuring the final retrieval delivers a complete, multifaceted answer rather than a singular repeated fact. Pure vector search also has blind spots. In e-commerce, a user typing red cotton kurta might trigger a mathematically similar result for a blue silk sari because the fashion context is technically close. The fix is hybrid search. The system runs a dense vector search for meaning, simultaneously runs a keyword search for exact terms, and unifies the results using a cross-encoder re-ranker. Even with perfect retrieval, packing too much text into the LLM triggers the lost-in-the-middle phenomenon. Researchers proved that AI models often forget the crucial facts hidden in the center of long prompts. Node 6 introduces contextual compression. The system surgically extracts only the highly relevant sentences from a broader chunk, discarding surrounding noise like website footers. Contextual compression reduces the token payload sent to the LLM, transforming a scattered data dump into a laser-focused prompt. At Node 7, we handle the prompt orchestration. It is critical to remember that every LLM API call is independent. These models are entirely stateless and possess no memory of the previous interaction. If a user asks a follow-up question, the system breaks unless we inject a conversation buffer memory, a running transcript of the dialogue, into every single API call. This orchestration handles massive logic tasks, like a student needing a summary of a 3-hour technical lecture. Sending 50 pages immediately triggers context limits. Orchestration frameworks execute a map-reduce chain. The system splits the giant transcript into 10 parallel streams, commands the AI to write 10 mini-summaries, and then reduces them into one highly accurate master document. This completes the journey to Node 8, generation, turning mathematical theory into a robust software product. However, sequential chains are inherently brittle. They operate on hard-coded assumptions that fail the moment a user inputs a poorly phrased query or deviates from the expected path. The ultimate test of enterprise AI is scaling for the real world. Consider building a voice-activated knowledge base for complex rural agricultural subsidies, where a farmer speaks directly in vernacular languages instead of typing. When an end user stutters, changes their mind mid-sentence, or speaks in broken syntax, a rigid linear pipeline cannot process the chaos. It also introduces a massive latency nightmare. Engineers must build streaming architectures optimized for time to first token and implement voice activity detection to instantly halt the AI if the user interrupts. To survive this chaos, the architecture must evolve into an entity that reasons through the data before it acts. The era of deterministic pipelines is giving way to the REACT framework, a system where reasoning and acting are dynamically fused. This autonomy begins with hypothetical document embeddings, or HYDE. The AI agent intercepts a bad input and autonomously rewrites it into perfectly structured prompts before searching. The architecture shifts from a straight line into a dynamic loop. You give the LLM a specific goal and a toolbox, containing the vector index, a Python calculator, and a live web search. The AI decides the sequence. The agent can query the internal database multiple times using its rewritten prompts, evaluate the responses, and mathematically merge the best results. In the Corrective RAG framework, an evaluator node analyzes the retrieved internal documents. If it detects the corporate data is outdated or irrelevant, the agent autonomously rejects the payload. Instead of producing a hallucination, the agent pivots away from the internal database entirely, triggers a live web search, and pulls the correct verified data from the internet. Giving an AI the autonomous power to evaluate its own retrieval data provides the final layer of control needed to suppress hallucination in high-stakes environments.